Hello, I now want to describe the inclined block with friction. And so you can imagine this situation where you've got a block here on an inclined plane, but the inclined plane can be pushed up. And as it's pushed up, you might increase the angle theta, and we want to find out what's the angle at which this thing is eventually going to slip and the block will begin to slide down the plane. So, how do we solve this problem? As with all these problems, we're looking at Newton's laws, and we're going to use this F equals ma equation. And what we want to do is draw the forces acting on the block. So I've covered this in a previous video, but I'll go over it a little bit quickly here just to make sure that you guys can view this independently. So here I draw a little dot. I'm going to do my force diagram. I've got mg acting downward like this, and I've got the normal force pointing upward such that it's perpendicular to the plane. So I've got these two forces. And as I said before, what we're concerned with here is the block moving down the plane. So we want to resolve mg into components such that one component is going to be pointed down the plane like this. That's the component down the plane. And this is the component that is basically opposed to the normal force. So this angle here is theta because of similar triangles. And as I said before, this component is going to be mg sine theta. And this component over here is mg cosine theta, as we've talked about before. So now if I want to work on the forces in the x and y directions, I can imagine a coordinate system that looks like this. We'll call that positive x, which is down the plane. And then just going perpendicular to the plane is positive y. So let's do it in, I don't know, the y direction. Let's look at the acceleration in the y direction, the sum of the forces in the y direction. And for that, I'm only concerned with this force here. That's the normal force pointing up along the y-axis. And I'm also concerned about this force here. That's mg cosine theta. That's pointed along the y-axis as well, but in the negative direction. So I'll say in the positive y direction is the normal force. And in the negative y direction is mg cosine theta. And that's going to equal the mass of the block times its acceleration in the y direction. So this is my equation for the sum of the forces in the y direction. Now, one of the things I want you to think about very quickly here is just to notice along this axis, the y-axis, is the block accelerating up and down like this? It's not. It basically stays balanced in terms of the normal force and mg cosine theta. They're both opposed to each other and perfectly balanced such that the block will not accelerate in y. It's only going to be moving down the plane like this. And because of that, the way we've set up our axes, it doesn't accelerate in y at all. And what that means is that down here, I can say this equals 0. The acceleration in the y direction is 0. And what that means is that the normal force minus mg cosine theta is basically equal to 0. All right? And that's fine the way it is. We can just leave it like that. What I want to do now is look at the sum of the forces in the x direction, and that should equal the mass of the block times its acceleration in the x direction. So let's redraw it here just briefly. So here's the plane, here's the box, like that. And pulling downward, we have this force that we talked about earlier. This is mg sine theta. Okay, so I'm going to label that mg sine theta as pulling it downward. Now what's pulling it backward? What's pulling it backward like this would be some force of friction. So the force of friction would pull that way. And remember that we've got the y-axis and the x-axis aligned like this. So we're only talking about things in the x-axis along the plane like that. So now I can write my equation. I can basically say mg sine theta, that's a positive force because it's operating down the plane. And the other force I have acting on it is friction, and that's going to be minus the force of friction, like that. And that's going to equal the mass of the block times its acceleration in the x direction. So this is a valid equation. Everything's good. But if the block is stuck, so if we're basically holding this at an angle that's not very large, the block would be stuck and it's just sitting there. It's not moving at all. But as we push this up more and more, then what happens is the block will eventually begin to slip and slide down the plane. like that. So right before it slips, before slipping, it's not accelerating in the x direction at all. And so I can say that mg sine theta minus the force of friction equals 0, or I can say mg sine theta equals the force of friction if I just add the force of friction to both sides. So I've got this equation here for things operating in the x direction, and I've got this equation here for things operating in the y direction. So all is well and good. And again, remember that this is the condition right before it slips. Now, just as it slips, let's think about that. Just as it slips, what's going to be happening? Well, if this block is just sitting there, that means that the force of friction is equal to the mg sine theta pulling it down. But once it starts to slip, then mg sine theta is going to be greater than the force of friction. So I'm going to now rewrite this equation. So as it slips, I'm going to get this. mg sine theta is just greater than the force of friction. So that's what we have. That's our equation. Now what I want to do is I want to write this force of friction in a little bit more expanded form. So I'm going to say mg sine theta is greater than the force of friction, but if it's just about to move, it's going to look like this. Just before it moves, this is the coefficient of static friction, okay? So as long as mg sine theta is greater than the force of friction, which is the coefficient of static friction times the normal force, then we'll get movement, okay? So this will be the condition for movement. Now, how can I elaborate this equation or make it a little bit more detailed so I can solve it or make progress with it? Well, I notice this, that the normal force appears in this equation, but it also appears in this equation that we had up here, this equation up here for the y. So I'm going to copy this equation. Let's copy this guy. And let's bring it down so we can see how it copy. Bring it down here. I'm going to place it here. Ooh, what did I do? Copy. Okay. And let's paste it right here. Okay, there we go. So what we notice from this equation that I just pasted is that I can basically rewrite it as the normal force equals mg cosine theta. Because this equals 0, I can just add mg cosine theta and bring it to the other side. And when I do that, I get this equation. And this allows me now to substitute. So here's the normal force, but here's the normal force too. So I'm going to take what is equal to the normal force, which is mg cosine theta, and I'm going to plug it in up here for the normal force. So let me rewrite that whole equation down here. mg sine theta is greater than mu static. And instead of writing the force that's normal, I'm going to write mg cosine theta because I got that from the previous equation. So I can substitute this in, mg cosine theta. I can write it like that. This equation is true right when the block begins to slip. Now I can work on it. I can say mg cancels out on both sides. So I get sine theta is greater than mu static cosine theta, like that. I can do more on this. I can divide both sides by cosine theta. Both sides by cosine theta. And, and cosine theta and sine theta. This sine over cosine is basically tangent theta because sine is opposite over hypotenuse and cosine is adjacent over hypotenuse. And so the hypotenuses cancel and it's opposite over adjacent, which is basically equal to tangent of theta. So the tangent of theta is now, going back up to this equation, tangent of theta, which is this term here, that's this term here, is greater than mu s, and that's canceling. Cosine divided by cosine is 1. So tangent of theta greater than mu static. This is our condition for when things will slip. So to be a little bit more precise on how to get the angle, what I want to do is I basically want to invert this equation. I'm going to say theta, if theta is greater than the arctangent of the static coefficient of friction, this is when we will slip, when slipping will occur. So just to review this very quickly, what we have is the block on an inclined plane, and we resolve it into the following forces. We resolve the weight into an mg sine theta going down the plane, mg cosine theta opposing the normal force. We set up an equation in y, looking at normal force and mg cosine. We look at this going in x, mg sine theta. And when it's being opposed by friction, we can set up an equation relating the force of friction to mg sine theta. And just before it slips, there will be no movement, and so there's no acceleration, so I get this equation. Once I get this equation, I can basically use it along with the previous equation up here that we got in y and perform a substitution, and when you grind it all down, you basically get this. That'll be the angle at which things begin to slip. And it's based on the static coefficient of static friction that gives us that. Okay, I hope this was useful to you, and I'll stop it now. I'll try to post another video next about the car on an inclined plane.